Hello everyone, in this video we're going to cover section 6.1 and 6.2, which is an introduction to exponential functions. Let's start by simplifying the following exponentials here in the warm-up. So keeping in mind that this is the product rule, when values are multiplying, their exponents will add, so we will have x to the fifth. Okay, so reminder that is the product rule. In B, this is going to be called the quotient rule. When values are dividing, their exponents are going to subtract. In C, we have something called the power rule. When you take a power to a power, those are going to multiply. We will have x to the sixth. In D, we have the negative exponent rule. We can rewrite this as 1 over 5 squared over 1 over 25, okay? We generally want to not have a negative exponent. If, for example, I had this, I could write it as 5 squared or 25. So I'll just say another example, okay? So similar to earlier, I could rewrite this as 4 over 1 squared or 16. That again is the negative exponent rule. Write the following with a base 10. So if we are interested in writing this with a base of 10, we would write 10 to the power of negative 2. Think about this being 10 squared in the denominator. If we want to write it with a base of 10 instead of as a fraction, we would do 10 to the power of negative 2. Similar situation here, this would be 10 cubed as a fraction, or we could write that as 10 to the negative third. The last section here, write with a base of 2, so we know that 2 cubed is 8, or we could write 2 to the power of negative 3. We know that 2 to the fifth to the fifth is 32. So we can write 2 to the negative fifth to rewrite that with a base of 2. Okay. If we're interested in describing the difference between x squared and 2 to the x squared is a parabola, okay? Whereas 2 to the x is an exponential, it is going to go up forever, okay? It never touches below 0, whereas quadratics can go below 0. If we want to sketch that graph, we can just plug in some random points here. So x squared is the first one, 2 to the x is the second one. You can just plug those points in. I'm going to switch colors over here. So 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. And then you'll notice that our values repeat even when they're negative. 2 to the 0 is 1, 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, and then if we do 2 to the power of negative 1, that's 1/2, and then 1/4 and 1/8. Okay, we're going to graph both of these functions as well. I'm going to change my colors here again. So here we have 0, 0, 1, 1, 2, 4. Okay, so that's your quadratic. We know what those look like at this point. We've worked with those quite a bit. And then 2 to the x. I'm going to go and start with 0, 1, 1, 2, and 2, 4. And then notice at negative 1, I'll be at a half, and then at a fourth, and an eighth. So notice that it is getting much smaller and closer to 0, but not actually touching 0. Okay, that's going to be really, really important for us. Let's talk about some basic exponential vocabulary. We talk about percent change. That refers to change based on the percent of the original amount. We talk about an increase in exponential growth when it's multiplicative, so it's doubling or it's tripling over it's something like that. Decay is decreasing by that rate, so we're cutting it in half or cutting it in fourths. The function itself in its most basic form can be written as 2 to the x. We can't use 1. 1 is 1 to the power of anything, is not going to change, right? It's always just going to equal 1. So I always use 2. We can define the domain and the range for this function. If you take a look at this graph on the right, it will tell you that that arrow is going to the right forever, to the left forever, but never touching 0. So that's going to be important for our range. For domain, we're going negative to positive infinity, whereas for our range, we approach 0, but never touch it and go to positive infinity. Okay. So for your end behavior, as x approaches negative infinity, y approaches 0, and as x approaches positive infinity, so does y. The equation of the horizontal asymptote is going to be y equals 0. So keep in mind this is the dashed line that we're not touching for the original function. And your y-intercept is going to be 0, 1. And that's always the case unless you have transformed the function. So I'm going to say for the parent function. Okay. Once we transform, obviously it might be different, but for the toolkit function, your y-intercept is going to be 0, 1. All right, let's take a look at the equation of an exponential function. We have f of x equals a times b to the power of x. A is the initial value. B is your rate. I like to call it the rate of growth or rate of decay. X is going to be your time. Sometimes we use t. They are interchangeable. We've already talked about domain and range. We've talked about the y-intercept. So something to note here is that the y-intercept is 0a. So a is your starting point. So whatever your starting point is, that is going to be the y value for your y-intercept. The base needs to be positive and not 1. We already discussed that. 1 to the power of x will always be 1. Okay. And it's not going to grow exponentially. If the base is greater than 1, it will represent growth. If it's between 0 and 1, it will represent decay. Now, if we're interested in solving or evaluating functions that are exponentials, we simply just need to plug in those points. Okay, so here I'm going to go ahead and plug in a 2 and solve. Keep in mind that I do want to simplify that exponent before I do anything else, and then I want to solve the exponent before I multiply by 5. Okay, it's not going to be 5 times 3, it's going to be 3 cubed, and that will be multiplied by 5. Okay, let's go ahead and find f of 2. So 5 times 2 squared plus 3, 5 times 4 plus 3, 20 plus 3, or 23. Okay. This is something that you'll see, especially in the homework and on any quizzes that you might have or exams, is finding the formula for an exponential function when you're given 2 points. So where you want to start is writing your function with general variables. Okay, and then I'm going to go ahead and plug one of those in. Okay, I know that a times b to the 0 is going to be a times 1. So that tells me a is equal to 6, which is great. Now I can take my second equation and plug in everything that I have. That's going to be divided by 6, which gets me 125 equals b cubed, and the cube root of 125 is going to be 5. So now I have everything I need in order to write the equation of this exponential. The next one is a practice problem. If you'd like to go ahead and practice it, go ahead and pause the video now. After that, I'm going to go ahead and continue working through these. All right, now I'm going to start with either function. I'll just start with the second one this time to just mix it up a little bit. I have 1 equals ab squared. I'm going to go ahead and solve for a and get a is equal to 1 over b squared. Unfortunately, it's not a nice simple number, but now I'm going to plug that in to my second equation. 6 equals 1 over b squared times b to the negative 2. That's going to be 6 equals 1 over b to the 4th. So I'm going to have b to the 4th times 6 equals 1, or b to the 4th equals 1 over 6. Oops. And then I need to take the 4th root of 1 over 6, which will be a gnarly decimal, and that is totally fine. Okay, that I can plug in into my original and solve for a. And a is going to equal 2.45. That gives me the equation 2.45 times 0.639 to the power of x. Let's talk about compound interest. This is a very important concept, especially if you have any sort of credit card or payments that build interest. It's very useful to know how these get calculated. So compound interest can be calculated using this equation. P represents your principal, which is your starting amount, or how much you initially owe, or how much you initially invest. N is your frequency of compounding, which means like how often are you making payments, or how often are you putting money into the account, usually monthly. T is time, and R is your rate. So for example, monthly, we'd say N is 12, quarterly it'd be 4, all that sort of things. So if we invest $3,000 in an investment account that pays 3% interest compounded quarterly, how much will the account be worth in 10 years? Here's all of the information that we need. Okay, let's go ahead and plug that in. A is going to tell us how much money we have in the account. So we have 3,000 times 1 plus your rate, always, always, always as a decimal, divided by compounding of 4 times to the power of 4 times 10. Okay, that leads us to A is 4045 with 5 cents. So after 10 years, our account is going to be worth $4,045. Take a look at this next one. Lily wants to set up an account for her new granddaughter. She wants the account to have $40,000 over 18 years. The account will earn 6% compounded interest semi-annually. And then how much does she need to invest in the account now? So that means we're finding P. We have A, we have time, we have the rate. Let's go ahead and plug in and solve. We're going to have 40,000 equals P times 1 plus 0.06 divided by 2 to the power of 2 times 18. Okay. What's going to end up happening is you're going to say P equals 40,000 divided by 1 plus 0.06 divided by 2, 2 to the power of 2 times 18. So if she wants to have $40,000 in the account in 18 years, she needs to go ahead and put $15,533.48 into the account today. Great. Let's talk about the number e here briefly. It represents an irrational number. The equation for it is in front of you. It increases forever without a stopping point. It's often used in a lot of real world exponential models. We can use an approximation for it, but generally we try to use the button on your calculator that represents the whole entire value. So try to avoid using the approximation if you can. If we're working with continuous growth, we're going to end up using E because E does grow continuously forever. So we have this continuous growth formula. I call it PERT. I usually write it with PE to the RT. It can be written either way. P would be principal, just like A naught would be principal. So A naught. Okay, it's all the same. R is the rate, T is time. Okay, if R is positive, we have growth. If R is negative, it represents decay. So that's the only fundamental difference between the rates in the compounding formula versus continuous growth. Okay. Notice down here we do PERT. Again, it's the same thing. A is usually used for money, P is usually used for other applications, but they do mean the same thing. Okay. Let's do an example. A person invests $1,000, it earns 10%, compound continuously. How much is in the account after 2 years? So that's going to be 1,000 times e to the power of 0.10 times 2. So in the account, after 2 years, we end up with $1,221.40. Another example here is decaying at a rate of 17.3%. That tells you that R is going to be negative. Okay, that's really important. We have 100 milligrams to start, and our time is now in days. So we have A equals 100 times E to the power of that rate times 3 days, which leaves us with 59.51 milligrams. Here are some practice problems for you. I would encourage you to go ahead and pause this video and start working through a couple of these now. All right, let's take a look. If we invest $1,500 in an investment account, it has 2.76% interest compounded monthly. How much is it worth in 12 years? That's going to be 1,500 times 1 plus 0.0276 divided by 12 to the power of 12 times 12, which will be $2,088.96. Number 2, you invest $2,000 in an account earning 7.5% interest compounded continuously. Oh, hold on. Let me double check my math on this really quick. I may have written the wrong number. 1,500 1 plus 0.0276 divided by 12, 24. This should be 15.85 and 3 cents. Apologies for that. On the next one, it is continuous compounding. So we have 2,000 times e to the power of 0.075 times 4, which is going to equal $2,699 and 72 cents. Then we have radon decaying at a rate of 2.1% per year. How much will we have in 15 years? So we'll say 1,000 E negative 0.021 times 15 is equal to the amount remaining, which will be 729 grams, 0.79 grams after 15 years. Finally, let's briefly look at the graphs of these functions. You'll notice that they look very similar, but their growth factor is ever so slightly different. Notice that they all do still cross at 0, 1 for their y-intercept. And notice that if your exponent is negative, it is a reflection over the y-axis. Okay, we'll talk about that here in a little bit on the next page.